Welcome back. So we're going to start where Mr. Palatasig left off with integrals. I do want to mention he talked about not memorizing some of the special cases of derivatives and integrals and rules that you should be understanding them. If you have the time to invest, I agree with him 100% that that is what we should be doing. But by all means, if you are under a time constraint, feel free to memorize those and go for the praxis. So, that being said, let's take a look at the limit definition. Mr. Pilotag has kind of jumped into the integrals, but we also have a limit definition of integrals just like we did with derivatives. In this case, we call it a Riemann sum. So from A to B, the integral of f of x dx we can define as the limit as n approaches infinity from I equals 1, the first case, the summation to n of f of x subscript I times b minus a over n, where x subscript I is equal to a plus b minus a over n times I. So let's kind of break this down of what we're actually saying. When we are looking at a Riemann sum, so let's say here's our function, who knows what this thing actually looks like, and we'll call this A and this B. We could estimate the area under this curve by using repeated shapes. So if we were to use let's say a rectangle, over and over again, we would start being able to guess more or less what the integral was. But we'd have a little error, right? It wouldn't be, rectangles don't perfectly line up with this curve. So what we do is we take the width of these rectangles, or whatever you want to call a shape at this point, doesn't matter, and we make them infinitely small in width. So this summation is going from the first shape that we're using to the infinite shape that we're using. So the width of each one of these rectangles, if they're equal width across, is going to be b minus a over n, infinite number of rectangles. So there's our width. And then we have our height, the function that we have, where we're looking at the current rectangle that we're looking at, right? So xi. So width times height would give width times height would give us the area of our rectangle, which is perfect. That's exactly what we want. In order to define the height, though, we have to know where we're starting, A. Then we need to know what rectangle we're looking at, which is I, and we multiply that by the width. The rectangle we're looking at times the width of each rectangle would give us our coordinate. We start at A to get there, and it's the function of it, which is going to give us our y value. So height times width, each rectangle summed for an infinite number in that range will have an infinitely small error and thereby give us the actual area under a curve. So when we actually go to do the quicker way of doing this, let's take a look at this function we have. We have the from 2 to 3 of negative x squared plus 6x minus 6 dx, and I've kind of guesstimated what this graph might look like over here. And they're asking from 2 to 3. So let's scroll down. If we're going to take the integral of this, then we can just apply the general rule, raise the power, and put it over that power. So negative x cubed over 3 plus 6x squared over 2 minus 6x. If we plug in 3 into this, we're going to get, for x, we're going to get negative 9 plus 27 minus 18, which equals 0. And then if we plug in 2, we're going to get negative 8 thirds plus 12 minus 12 equals negative 8 thirds. So let's discuss what we actually are doing. What we're doing is we're taking the area under the curve from 3 back, and we don't want all of it, so we're going to subtract the piece that we don't need. We need between 2 and 3. So if we subtract from 2 onwards, we should get our area between 2 and 3. So 0 minus 8 thirds is equal to 8 thirds. And that, in fact, is true. That is the area under this curve. So that is how we find an area when we're looking at one function. When we look at two functions, we do a very similar idea. And there's a proof to this, but we're not going to go all the way into proving this. We're just going to use it. So we've got f of x equals x squared minus 2x plus 1, and g of x equals 2x plus 1. So if I were to guesstimate what this graph is going to look like, we've got y-intercept there, 2x, okay, so it's going to look something like that. And then our other function's going to be something along these lines. And they want to know from 0 to 4. So there's 4, and this is 0. So I've actually calculated this out already. This point here is actually going to lie right on the y-axis. So we'll keep that in mind. But we're going to take the integral from 0 to 4 of... Okay, so when we do between two curves, as long as there's not an intersection in between these 2 points, we're fine with using this rule. So we're going to do, the rule is, let's just put that right here, a to b f of x minus g of x dx. So we can subtract the functions from each other and then apply the integral. It doesn't matter which one we choose first, as long as, like I said, we don't have any kind of intersections in between. I discussed this in the memorization piece about what to do in that case. We'll talk about it after. So x squared minus 2x plus 1 minus 2x plus 1 dx. If we do all of that out, so x squared minus 2x plus 1 minus 2x minus 1, we're going to end up with x squared minus 4x. Take the integral of it, x cubed over 3 minus, so 4x is going to become 4x squared over 2. That's going to simplify down to 2x squared. Now we can plug in our values. So if we plug in 4, we're going to get 64 over 3 minus 32 And if we put that over 3, multiplied by 3, we're going to wind up with negative 32 over 3. So we know that this has to be positive, given that we're talking about an area under the curve. So the actual answer is going to be 32 over 3. The reason I didn't plug in 0 is because we don't have any constants here in our integral. So plugging in 0 would just be 0, and that would be pointless to subtract that from it. But remember that this needs to be a positive answer, so the actual area under that curve is 32 over 3. Now, getting back to what I was talking about for if there's more than one intersection, so let me just create a situation like that. If we have this function and we have this function, and they want to know from A to B what the area is under the curve, or I'm sorry, what the area is between these two curves, so this area right here and this area right here, you need to break this up using the methodologies that I've been showing you. So you would take and find the area between A and our new point C, and then the area between C and B, and add them together. If you want to learn the other methods to this and the more complex, you can look those up on your own, but this is going to be the quicker and easier method for you. And even this I doubt you will see on the praxis. 9 times out of 10, you're going to be looking at a situation like this one here. So, that being said, let's move on to a use substitution problem. I did have one in the memorized sheet as well, but just so we see another example of what to do here. If we want to find the integral of 3e to the 3x dx, first of all, we can pull out the constant. So 3e to the 3x dx. Now, we can define u as 3x, and we need to get rid of this dx as well. So du, so the derivative of this would be just 3, right? If x would be the 1 power, pull that down, we'd be left with just 3 times x to the 0. Anything to the 0 power is 1. So 3 integral of e to the u I apologize, I didn't finish this out. I got sidetracked. So we needed to get rid of dx. So we go back up here. We didn't actually finish this out. So du, derivative with respect to u, is going to be 3dx, and we need dx by itself because that's what we're trying to substitute in for. So du times 1/3 is equal to dx. So now I can put my du here. So times 1/3 du, because we're getting rid of this dx. Again, we can pull out our constant. So if we pull out the 1/3 to here, we're going to get 3/3 e to u du. And we can do that. We know that E to the x is just e to the x. So that same rule applies. 3 over 3 just becomes 1, so that gets eliminated. And we are left with e to the 3x, and then we add our constant. And that would be our answer. So just to walk through that one more time, because I got sidetracked right up there. We're taking the integral of 3 times e to the 3x dx. We pull out the constant, and we use u substitution for 3x. We take the derivative of that. There was 1 up here, so we pull that to the front. X to the 0 is just 1. And we need to be subbing in for dx. We can't be having a u and a dx. That doesn't make sense. So we're going to get dx by itself. So we need to multiply this side by 1/3. Now we can sub in for dx and put u for 3x here. Pull the constant 1/3 out. 3 over 3 cancels, because it just becomes 1. And we know that e to the x is just e to the x, which in this case we're calling e to the u. So we take the integral and we have 3 to the x substituted back in. So e to the 3x and then plus our constant. So that's another instance of use substitution. Again, there are a ton of uses for this. We're not going to go into all of them. However, you will likely see one use substitution problem at best on the Praxis, and most of the time that I hear about it, it is using E. So that should cover your bases. Next, we're going to take a look at integration by parts. I have not heard of anyone having this type of problem on the Praxis ever, but we're going to go over it just because theoretically it can be on the Praxis. So if we want to have the integral of 2x plus 1 times 3x squared dx, we're going to apply our integration by parts. So the formula for that is integral of f of x g prime of x equals f of x g of x minus the integral of f prime of x g of x. So let's define what all of this here means in terms of this. So if we're going to apply this to here, then f of x would be 2x plus 1. We know that this term here has to be what we're considering g prime of x. That's what we have right here. So g prime of x equals 3x squared. We can then define f prime of x. That's a constant, so it's going to get eliminated. That's x to the 1, so we pull the 1 to the front. 2 times 1 is 2, times x to the 0 is just 1. We get 2. And g of x, we're going to take the integral of. So we're going to make this higher by 1 and divide by it. So 2 plus 1 is 3. Divided by 3, 3 over 3 cancels, and we're left with x cubed. So now we have all of our pieces defined. We can plug in. So f of x is 2x plus 1. That was a little too ugly. 2x plus 1 times g of x, which we decided was x cubed, minus the integral of f prime of x, which is 2, times g of x, which we decided was x cubed. Okay, so we can multiply this one out. That's going to be 2x to the fourth plus x cubed minus, and we're going to pull the constant out, 2 times the integral of x cubed, so that's going to be raised to the fourth, and then we're going to put it over 4. So this negative gets the negative is going to get distributed through. So negative times 2x the fourth over 4. And we can simplify that to be 2x to the fourth plus x cubed minus 2 over 4 is 2. We have x to the fourth over 2. We can put this x to the fourth over 2 as well by making this 4x to the fourth over 2. 4x to the fourth minus x to the fourth. Well, here, I'll just show you. Fourth over 2 minus x to the fourth plus x cubed, right? So we just put them over the same denominator. And to do that, we had to make this a 4 instead of a 2. So our final would be 3x to the fourth plus x cubed. That was over 2. And like we always do at the end of our integrals, plus c. And there's our answer. So really, the trick to this, I mean, most of this is not new information for you. It's defining what these 4 items are over here at the start. So if this is our function, we need to think about what our integration by parts formula is and realize this is f of x, this is g prime of x, figure out what the derivative of x is, and take the integral of g prime of x to get back to g of x. And then just plug in all of the pieces as we did, solve, and plus c for the finish. And that should cover it for this lesson. We did integration by parts, u substitution, area between 2 functions, and area under a curve, and we touched on Riemann sums. Thank you.